pleased to introduce Alex Sadovsky, who will be leading a talk titled Where We're Going, We Don't Need Computers, End-to-End Serverless Data Science. Alex is a Senior Director of Data Science for Oracle Data Cloud. A computer scientist turned neuroscientist turned data scientist, Alex pioneered supervised learning approaches while at Datalogix to help target online advertising on social media platforms via offline consumer spending habits. Since the acquisition of Datalogix, he has focused on marketing data science initiatives for audience advertising products across the internet. Please join me and welcome Alex.
Awesome, thank you. Cool, so today I'm going to talk about serverless computing. No real reason behind that other than I think it's kind of cool. So I was asked to give a talk and I thought about things I thought were cool. Serverless is one of them. It's helped us a lot at Oracle Data Cloud. So I just kind of want to talk about how our journey there today. So first off, what is the Oracle Data Cloud? So basically, Oracle Data Cloud is the combination of 5 different startups. Oracle, in a lot of ways, is a tech holding company, and they said, hey, we really want to get into the marketing space. And so they ended up making acquisitions in the space. And so really, it's 5 strategic tech startups that all have come together to form kind of the Oracle Data Cloud. And essentially what we do is we try to unlock the value of data to help advertisers connect more deeply with their customers. And really, when you think about this, in a sense, we're advertising. But what we really, our kind of dream is advertisements don't have to be creepy, don't have to be mistargeted, et cetera. The more that we can work with data, the more that we can work and understand individuals and clients, we can help get information and get advertisements to the right people and get the right responses from that. So we have a ton of data. Our data is scanning the entire globe. We have over 5 billion cookie IDs, 1 billion mobile device IDs, so like your iPhone, 15 million domains, and 1.1 trillion page views. So we're bringing in this data constantly. It's constantly coming in. Additionally, it's not only online data. What we find is that kind of online persona doesn't always match what you're doing offline. An example of that is every 15-year-old in the world is looking at like Ferraris online, but the people who buy them aren't usually 15-year-olds. And so we also tracked in-house spending. And so we have 115 million US households, and we have things like the kind of automobiles they're driving, what they're buying in the grocery store, what they're buying in the mall. And we actually captured $3 trillion of annual spend there. So overall, this kind of gives us this full view of a consumer. We know what they're buying, we know who they are, we know what they're doing online, and we also know kind of location data where they're going. And this is down to an extremely detailed level. And the reason I'm going to talk about all of this is just we have a ton of data, and we can't throw any of that data away. Every kind of model that we're running, we need to kind of look at all of this data we have and figure out what's unique to the specific model that we're working with. And so for an individual, we might know kind of different things about their, if they're married, if they have kids, what they're buying in the store, what they're doing online, et cetera. And so we have all of this data, and we have to do something with it. So this is where machine learning comes in. We use machine learning at the ODC to go from targeted advertising down to reaching the individual on a platform. And the way that it works is this. We start with some sort of event or some sort of action that we want more of. And so this could be people who are past purchasers of a product. We want to increase their purchases, people who went to a specific website, people who are clicking on an ad, et cetera. A client comes to us and they say, we want to sell more of X, or we want to see more of X happening on our platform. So they come to us with that, and what we partner that with is all of our data. And we use machine learning to kind of bridge that gap. And so someone says, here's clickers on our website. We take all of that data I just talked about, and we kind of dissect what is a clicker. And a clicker doesn't have to just be one profile. Maybe if you're a suburban dad on the West Coast and you have 3 kids and they're all enrolled in soccer or something like that, maybe that's a clicker. But then maybe also there's millennials on the East Coast or some other sort of aspect. And so what we try to do is use machine learning to take all of this data, figure out patterns that we see in behaviors that are happening in the world, and put them together. And from that machine learning, it generates a model. And that model is essentially, here's a model of how data about individuals translates into a behavior. And we use that model, and we'll score the entire internet on cookies. We'll score the entire United States and households. And we try to figure out which cookies, which households are going to be the most likely to do that behavior in the future. Next, we have this idea of an ID graph. We have to reach those individuals somewhere. And that's how we then hit people on different social media platforms, on the web, et cetera. And we get ads essentially to them. And then the whole cycle kind of repeats again. We measure it. We figure out were we successful or not, and we continue. So we achieve success by doing this on a serverless data platform. And so every month, we're creating 10,000 plus models. And each model has terabytes of information. We're not reducing our data set down from the beginning, and so we have petabytes of data, but each model is kind of turning into terabytes of data that need to be processed, and everything needs to be accurate. We're not the only kind of players in this field. And so all of our models are very transparent. People are using models. If we're trying to figure out who soccer moms are in California, another company is doing the same thing. And if our models don't work well, our customers will notice. And so really, we have to worry about, we can't cut corners here. We have to use as much compute power as possible. So this platform that we put together has these kind of following constraints, which make a lot of sense. One, data size and variant. And I'll go into that a little bit more later, but data is always changing for us. We're always making strategic acquisitions. We're always trying to figure out what kind of data could fit in different gaps. And our data just by nature is always changing. So our platform needs to be invariant to kind of changes in data size. It needs to be scalable by load. We don't always have like a steady stream of requests coming in, and I'll go into that too. We might have a double the amount of requests one month for whatever reason, and so we need to be scalable in that sense. And while we're being scalable, we need to be conscious of customer SLA. If we get twice as many requests one week, we can't just kind of say, oh, you have to wait twice as long for your models. So jumping into our talk title. So originally, where we're going, we don't need computers, end-to-end serverless data science. This was a Back to the Future reference, as you can see by the DeLorean here in the photo. But much like in Back to the Future, I showed this to Oracle Legal, and they said, yeah, we don't own copyrights on that. You cannot do a whole talk that is Back to the Future themed. It has this 80s aesthetic. So that all kind of faded away, much like the photo in Back to the Future. So we'll throw out an alternative talk title here. Serverless computing, so easy, even a data scientist can do it. And that's because I'm not a DevOps engineer, I'm not a data engineer, I'm a data scientist by trade. And so for me talking about this, I feel like I can talk about it because it was so easy that even myself and my team could put it together. So what is a data scientist? You probably have seen this kind of Venn diagram where there's math, software engineering, business, and like data scientists live in the middle there. Reality that I see in a lot of organizations, including my own and many times, math, maybe you do a dot product, that's good, but that's about it. Stack Overflow kind of replaces any real engineering chops. And then finally, like business is you're just like, how can I make a plot that even our sales guys will understand? It's a bar graph, come on, like one side's bigger than the other. So why do we have this reality? Really, I think that a lot of it is because there's more to the Venn diagram than what we're showing, especially in a very serverful world. Data scientists often are asked to wear many hats, especially in startup organizations, and they're not essentially able to just focus on what is data science. So a lot of data science, especially many organizations I work for, random fire because some resource is overloaded, broken, et cetera. When something breaks, even if you're a data scientist, you're still responsible for making it work. Setting up and maintaining infrastructure, ideally there's whole teams to do that, but that takes time. And so a lot of times a data scientist is like, oh, I have to spin up all these boxes myself. I have to kind of set up our whole infrastructure for making real products work. And then the last one, figuring out how to install machine learning libraries, install different software, how to take their code that was running perfectly on their laptop and now it doesn't work in production environment, all of that sort of stuff. And so kind of the hope here is that serverless tech can replace a lot of these. And that's really like what drew me to serverless tech initially, is that if serverless tech replaces a lot of these, then we can start having like data scientists actually read papers and write papers and do more intense math and do better engineering and kind of focus on other aspects of the business. And so that's really what kind of drew me to data science and serverless data science specifically. So today's going to be a case study. We're going to start with a real-life, made this word up, serverful data pipeline that was actually in production for Datalogix about 4 years ago. And this is something that I built up initially, and this is actually even pre-cloud, and so it was just all like kind of serverful, lots of computers, not kind of exploiting a lot of the serverless and cloud computing that we have today. So then we're going to go through this pipeline. I'm going to try to recount some real stories, little fiction thrown in there too, of how we broke this along the way. And so we were using server-backed approaches and what went wrong. Next, we're going to build up serverless solutions. So we're going to take all of those problems. We're going to say, if we were serverless, what could we have done to make this better? And kind of the last point here, everything today is going to be cloud agnostic. And so not focusing on a specific cloud provider, basically ideas, we're going to focus on like serverless ideas, and you can go apply those on whatever cloud can kind of support those. So here is our serverful data science platform. And I'm going to walk you guys through it because we'll be coming back to this a lot. So really, in our case, we're doing supervised learning, and we're doing batched model requests. And so our use case is very specific, and a lot of the stuff I talked today might not apply to every single use case. But for us, we have these requests that come in, and we have probably 3 or 4 hours to run them and then get kind of results out the door. And so essentially what we start with is a user here. A user could be like an upstream system as well. It doesn't have to be an individual. But someone's coming in with a model request, and so they're saying, hey, we want to sell macaroni on the internet. Model us up some macaroni. That's going to come to some sort of API server, which is essentially like a RESTful interface or something saying, hey, I'm posting a job. I want you to run a model for December macaroni sales. Go do it, modeling system. And we're going to ignore this piece right here, but you can kind of think of it like sometimes you have jobs that run on schedules. And so, typically the data science way to do it, or any way to do it, is you throw it in cron or some sort of scheduling machine, and every week it's running a model, et cetera. So from the API, we're going to hit a workflow machine. And I'm going to go over workflow a little bit later, but the idea is modeling is more than just run a model. It's preparing multiple data sets. It's maybe massaging that data in certain ways, and then running multiple models, putting those models together, et cetera. And so that's where workflow comes in. After that, I have this kind of ubiquitous catch-all ML machine. And really what I'm going to kind of throw in that box is any type of machine learning that can be done on like a single box. So this could be maybe a GPU instance running deep learning. It could also just be running some models, some tiny like little models, anything that doesn't really require a full cluster to run. But attached to that, we do have our cluster. And so we have a Spark Hive cluster. And so this is if we want to run models on a ton of data, we're going to need to reach out to Spark. We might want to run some of those models in Hive, et cetera. And then everything else is kind of data. And so when you think of big data, we had a data warehouse. We used to have these giant proprietary data warehouse machines. And that's housing all of our kind of petabytes of data. We have a results database. This is probably going to be something that downstream users are hitting in some case. And then we also have like a results cluster. So in our case, results database might store some metadata about the modeling that we ran. And results cluster is maybe a Hadoop cluster. It's maybe some other sort of file server. It's basically just a way to say, in our case, we're sending out audiences. Here's 20 million individuals who should be targeted. It's just a place to kind of store the results from our model. So this was our setup. And it works pretty well when it works. And so we're going to spend the rest of the time kind of dissecting where it breaks down and how we can go about fixing that. So we're going to start right here at the beginning, the API server. So this is kind of a brief allusion to clerks. This job would be great if it wasn't for the users, right? Models, all of these systems are great if you don't have any other people using them. And as I said, users can be like upstream systems, et cetera. We're going to dissect a series of unfortunate events that broke our production here. But before we do that, I'm sure many of you have heard of the butterfly effect before. As illustrated here, butterfly is flapping its wings. It causes some disturbance in the airstream. And in Texas, thousands and thousands of miles away, because of all these interconnected events, you have a tornado. And here the butterfly is very happy with its results. But essentially, the idea behind this is when you have a very connected kind of complex system, little changes that happen all over the place can have major effects. And so kind of diving into that a little bit deeper, there's this idea of chaos engineering. And this book's actually free out there on the internet. I suggest everyone read it. It's a cool approach towards engineering. But the idea is you have all of this kind of computing really has become like this complex adaptive system. And you have all of these interacting components. And so when you have everything that's super distributed and super kind of loosely coupled together, there's a lot of stuff that can go wrong that you never would expect in testing. And so what went wrong for us? So kind of jumping back here, we had a system upstream break. And it turns out we wrote this system never expecting two things to happen at the exact same time. And now all of a sudden we had like 1,000 requests all at the same time. Requests are getting dropped by the API, et cetera. Some of this turns into kind of bad data science programming. Initially, this was actually not even multi-threaded, and we found that out the first time. And so it turns out when you're running Flask, you have to go in and set some multi-threaded parameter. Someone didn't do that. And so literally when two things hit at the same time, it would either time out. It was bad. So that's like, OK, so you can fix that. Again, it's data scientists, though. And like, really, should data scientists be writing multi-threaded web servers? Maybe not. And so we have that sort of issue. But then you can also just think, we've had bottleneck events upstream where results, multiple things. We're only supposed to be getting maybe 100 requests, 1,000 requests a day, 10,000 requests, whatever. And sometimes it's like, oh, that system was down for 2 days. And then that team calls us, and they're like, hey, great news. We got our system back up, and we just sent 5 days worth of load over to you. And it's just like, all right, this thing's going to break. So there's different ways you can kind of adjust to that. In some ways you can put load balancers in front of your systems. And that's kind of, load balancers in themselves, depending on your cloud provider, there are serverless solutions to that. And that's kind of cool. So it kind of mitigates the problem. You have this load balancer, but you still have two computers there. They're very server full. They're very much computers sitting there. And so if you put a load balancer and you put two boxes there, maybe they're tiny boxes, and you start testing it, still, when you start stress testing it, you're going to break it. Again, you can definitely hit the system with tens of thousands of requests and break it. And the whole idea of the chaos engineering sort of principle is like, get prepared for all of this sort of weird stuff and build your systems so that they're robust, that things are going to break in ways you never really expected them to break before. So there's other cloud solutions. You can start putting autoscalers. You can start doing all of this sort of stuff. But now, like, really, what my biggest worry is you're focusing a ton of time on just writing a very simple API that is just like a REST call saying, post, run a model, go do something. And now you have this multiple group, it's going to size up, et cetera. And even once you get the kind of auto-balancing or auto-scaling here, there's still problems that can happen. And so, there's still data scientists at the end. We're still humans at the end of the day. And so you release a new code release, and you want to update your kind of API. If you don't have a good kind of stage dev system and all of that sort of stuff set up, do you do it in production? Do you just shut it down for a few minutes? What do you do there? What if you actually break your code? Is the API going to be catching it, et cetera? So you can break this system very easy. So the solution and all of the serverless stuff I talk about today is going to be like incredibly simple. But the solution is use API as a service. When we first started working, API as a service didn't really exist. But when we moved to the cloud, API as a service is basically a cloud service that just says, oh, you want a simple API? You can go into a kind of graphical user interface on the web, set it up, say this is what we're looking for, and in seconds you have it there. And pretty much guaranteed, whatever the one from a cloud provider is out of the box is going to be better than most people even working for months on a similar sort of project. So kind of diving into this magical little black box that we replaced tons of computers with, set up in minutes, not weeks. So you're not writing code, you're not doing anything. It's really kind of like click and point, set up an API. Scalable to hundreds of thousands of calls. So what's cool about serverless computing is you take all of those problems of load and all of that, and you throw it onto your cloud provider. And basically, the cloud provider has to figure out how they're auto-scaling in the background, how they're kind of taking in all of these requests. You don't really worry about it. You're basically just saying, hey, I want an API that can respond to these sort of things. And you put that all on your cloud provider. And so for a data scientist, and this is going to come up a lot again today too, you focus on business logic. I want my data science team just saying, hey, we want to have a request that comes in this way. We want some new config parameters coming in. I don't want them having to think about how do you code up a good API that's resilient. Another one is hiring. And so a lot of companies create their own crazy internal systems. And then when you hire someone, you're just like, oh, this is our weird like Project Oyster system, and it does all this crazy stuff, and here's all this documentation and stuff. You can hire someone off the street, and depending on your cloud provider, they're probably going to know exactly how everything works. And so that's a pretty awesome thing too. And for us, it just works. It's 100% uptime. These services do go down for cloud providers, but usually depending on your cloud provider, if your cloud provider is having problems, the rest of the internet's having problems too. So it's not that bad of a day. And so for us, using sort of an API service as opposed to kind of rolling our own constantly was super helpful. All right, so we replaced one computer. Are we good now with our serverless architecture? The answer is definitely no. So we're going to dive in. We still have this guy right here, our kind of cron scheduler machine. So with this, it kind of comes the sad conclusion. Every computer breaks. As time approaches infinity, every single computer will break. Computers are physical, and so even if you're on a cloud provider, there's going to be hard drives that are failing, there's going to be motherboards that are failing, you're going to get a message from your cloud provider saying, hey, could you please restart this system because we're detecting hardware events or something like that. So computers break. Software in OS also breaks. They need updates, they need restarts, they need security issues, all sorts of stuff. And so software additionally breaks. So everybody kind of has these machines in their organization, and everybody has them, and they're just like, oh, that machine just runs X. And sometimes they have like a clever name for it. This is the whole idea that your cloud computers should be cattle, not pets. So you really shouldn't be naming these computers. But we always have that. We have that in our system too, where we're just like, oh, I love that box. That box just runs this, and it's done it for 2 years. We really hope it doesn't break because the guy who set it up left. But what could you do if you could just run X without worrying about the machine it runs on, right? All you really care about is X. You don't really care about the machine itself. The computer, there's nothing magical about it. It's just running some piece of code, and it's lucky that it's run that code for a couple of years. And so if we want to just run code, the idea is just run code. And so this is where like different code as a service sort of platforms roll in. And so if we can actually just run something that runs some code for us, and in this case it's like a cron scheduler, we want to run some little bit of code every single week, then let's just do that. So kind of diving into there, serverless compute, we can focus on code and not computers. And the cool thing with serverless compute is it's very event driven, so you can hook it up to different events. So maybe every week we get a file drop and we want to process that file and then go kick off a job, or maybe every week some ingest team finishes doing something and we want to kick off a job, et cetera, et cetera. We get some requests from some hotline. Serverless compute lets you just kind of have these little, very loosely coupled pieces of code that are connected to events in your system. And it doesn't have hard drives, motherboards, et cetera. I mean, it does somewhere, but that's magic and in the cloud, and you're not worrying about it. You're just saying, hey, cloud provider, I want to run this code right now, make it happen. Additionally, for us is we only pay for what we use. And so for our use cases, we're not running a lot of jobs 24/7. A lot of these things are only in relation to specific events. So if you kind of SSH into different machines on your network, and you see a lot of stuff like this, where the machine's pretty much sitting idle 24/7, or at least most of the day, then you're actually paying for all of that. And if you're reserving a machine for a year, or taking it like on demand for a year or something like that, you're actually spending a lot of money. And so for us, serverless compute can actually be a cheaper way to run a lot of our processes. And again, it's super scalable. If we wanted to multiply our workload times 10,000, as long as we're willing to pay for it, we can do it. All right, so we have kind of this little serverless aspect now. Now I'm going to talk about serious compute. And so serious compute I'm referring to as our machine learning machine. In an ideal world, everything would be serverless compute, and I'd be able to just say, hey, I want to run this sort of stuff. The problem is there's some limits on different kind of code as a service systems. A lot of it is runtime, under like 5 minutes or so, memory constraints, even language constraints, et cetera. So now what we want to focus on is how do we deal with like kind of this machine learning machines? How do we deal with compute that's a little more serious? So we're going to dive into there. And really the answer to that for us is going to be containerized compute. So we're going to jump in. So containers. So many of you, I'm sure, have heard of Docker. There's other flavors of containers, but I think Docker is definitely kind of the most popular at this case. And really, you can think of containers as these isolated, fully contained, like little mini systems. If you've ever worked with virtual machines, Dockers are kind of similar to a virtual machine in concept. They're a little more lightweight, though. And you can kind of think of serverless compute, so what we were just talking about, but it's on like a bigger scale, and you're not just controlling just a little bit of the code, but you're actually controlling the OS and some other aspects around it. And so it's bigger deploys. And so Docker, you have your code, you write it, you put it in containers, and now you have to deploy those containers somewhere. And so there's a couple different deployment systems. One is Kubernetes, which is a talk in another room. So if you guys are actually all missing out on that right now, yeah, you can leave if you want. But that's an awesome system. Mesos is another one. These are cool, and depending upon like your organization setup, it sometimes can make a lot of sense to have your organization set up one of these. And then the idea is that some infrastructure team is running a Kubernetes cluster or Mesos cluster, something like that, and you're just kind of deploying your package containers on it. Additionally, though, cloud providers also offer their own serverless compute, so they have container services. And essentially, these are really cool. You build all of your code, you put it in a Docker container, and then you just say, hey, I have some code, and it needs 4 processors and 2 gigs of memory. Cloud service, go run that somewhere. And you don't care what computer it's running on, but you basically just say, as long as it has those constraints, I'm going to be happy. And so again, it's really cool. It lets data scientists focus on kind of the code itself and the constraints of the code, and not really worrying about, oh, this computer, I'm going to have to share it with that guy, and so I'm going to have to call him on the weekend because I want to run a job that uses this many CPUs, et cetera. So it lets us kind of cheat. So we took a lot of our machine learning sort of platforms and we put them in containers in our machine learning code. And so now we have the kind of these deployable containers that we can go out to our cloud provider and say, hey, we need to double our load. We need twice as many containers today. So we still have workflow in here. I kind of skipped over that. So what do we do about workflow? So there's an easy way that we can kind of cheat. Now that we have containers, if we really wanted to, we can kind of just throw everything in a container and we kind of succeed. And for workflow, there's a lot of cool different services. There's Airflow, there's Luigi. I actually have some talks on both of those. I think they're really, really cool for workflow. And those we've actually had successes putting them in containers, and that's how we actually run our production nowadays is we have containerized workflow. And so the workflow itself is running in a container, maybe on the same machine, maybe not. But basically, we're able to have these workflow containers that help orchestrate the rest of our tasks. But the cool thing with serverless tech is more and more tech that is serverless is becoming available. And so I kind of want to dive into this workflow a little bit. So what is workflow in reality? I've talked a bit about it, but when you think of data science and like a modeling, kind of standard modeling pipeline, you start with some data. You're maybe playing around different IDs or different transforms on it. You're creating different variables and features. Maybe you're reducing them. Maybe you're running some models. And then you do the same sort of thing and you score your universe. In reality, though, it's not always a straight line. There's parallelism within there. And to be fast, you want to exploit that parallelism. And so like while you're building your data and doing all your stuff on your modeling side, you have your ultimate kind of data you're going to score. You can start building that in parallel. And in reality, here where I have all these little boxes, maybe you're running an ensemble, multiple models that can run at the same time. Maybe you have multiple data sets, et cetera. And so this is really where workflow comes in. And this is maybe like what a typical kind of stripped down workflow would look like. And so if anybody has a kind of formal data science or a computer science background, you probably remember state machines. And you go and you get a computer science degree and you think you're going to be programming all the time and you're learning like formal logic and state machines and things like that. And so this is like a typical state machine for like a video game or something like that. Someone clicks pause. It's essentially Markovian in the sense that only the current state that you're in matters. And you basically have these little paths. And so what's really cool is different cloud providers are looking at this, and they essentially said, hey, we can make a state machine that's serverless. And so they have state machine as a service, which if you look back to kind of our graph here, this in a way is like a state machine. It's actually like even simpler than that. It's a feed-forward graph. And so cloud providers have started to put together serverless state machines, meaning that you can basically set up these kind of connections that we have for the model over here all on a serverless platform, saying I want to run A first, and then I want to run B, and then if B fails, I want to go to C, but if B succeeds, I want to go to D, et cetera. And so while we're actually not doing this today, this is kind of newer services, there's different state machine services out there as well, and moving to those also kind of helps you go more serverless, because even when we're running Luigi or something like that, containers can still die. We still have to focus on the logic of how do you run a workflow system, as opposed to how can we just run some cloud system that we don't have to worry about and let kind of the data service provider contain that for us. So again, kind of getting back to it, we don't want to reinvent the wheel. If there's some serverless tech out there and it's not too hard to use, we want to focus on that so we can get back to kind of business data science logic. All right, big data. Everybody loves talking about big data. And so we have our big data, I'm going to say, is everything here. So we have data warehouses, we have result databases, we have like these file systems and Hadoop clusters and all of that sort of stuff. This is probably the only time you'll ever hear someone from Oracle say this, and this is very unique to our workload. But for our workload, we don't use databases at all. And so we're not doing joins. We're doing joins, but we're not having these big, like, old school relational databases where we have multiple joins to do, et cetera. And so we actually replace all of our big data with something that probably anybody who uses cloud is using today, and that's just an object store. And so basically your kind of bucket for storing files, that's our database for everything. So this is how we do it. So our data lake really is just an object store. So object stores, if anybody's using cloud, this is the most common serverless part of cloud. And this is why serverless is so cool. Like, everybody loves their object store. You think about it, you're like, I have this bucket that I somehow put data into, and I can put as much data as I want, and somehow it always gets bigger. And I can have my entire company access that data at once, and I don't have to worry about it slowing down or things like that. It just kind of magically works. And so when you think of serverless, kind of start there, think of the file system. The way that we got rid of using databases is we store all of our data that we have in object stores. And so it's in a partition format, which allows kind of scans over it to be quick. We use Parquet, so the schema itself is kind of located in the data. And so we have all of our data, or our databases are essentially flat files within the object store. And then we build data on top of it. So you can use Hive, you can use Presto, you can use Spark, and you set up externalized kind of databases on top of all of this raw data. And what's really cool is as we work between different orgs, my org can be using Hive to work on this data, another org could be using Spark, a business analytics org could be using Presto. They're all working off the same sort of data, and it's not like they're working off different databases in different realms. And that said, I mean, databases still have a use case. We have some use cases for NoSQL. We have some use cases when we have lots of joins and things like that to use a traditional relational database. But for big data, we've kind of gotten rid of using databases themselves, and we're all in the object store now. So we have pretty much everything built up, and then we have our last piece here, Spark, Hive, and Presto cluster. And for sake of time, I could go into this a lot more, but we're going to make it really easy. Surprise, surprise. There's a lot of managed services for these things. If you haven't heard of Kubel, that's one of them. So they're a managed service that handles all of these. Additionally, there's starting to be serverless options for these as well. And there's different use cases for them. And so there's a serverless Presto now. What's cool about serverless Presto is you just say, I have a query. I need it to run somewhere. I don't care. And it's just going to charge you on how much data it's using to kind of scan over to complete that query. But basically, you don't have to spin up clusters, et cetera. There's managed approaches, which aren't 100% serverless, but it's the same sort of thing. And for different workloads, we have specific workloads that are basically 24/7 running. For those, a serverless kind of approach is actually more expensive for us. And so we use more of a managed approach for that. But you can think of serverless as maybe more ad hoc queries, et cetera. And so I think that exists for Presto today. I think more and more there's going to be serverless Spark, serverless Hive, et cetera, as time goes on. And again, the nice idea is you don't really have to worry about setting up the cluster yourself. You just have to worry about the queries and the business logic that your company needs. So here we are. So this is kind of the end of our serverless journey. So we started with this, lots of boxes, lots of actual physical computers, lots of points of failure. And we ended up with this kind of serverless setup. And what's really nice is now everything is kind of contained. It's all built on somewhat like commodity sort of solutions. It's not all these custom one-offs. And we really have an awesome system here. And so I'm going to go through some scenarios that kind of go through how this is helpful for us. So these are real-life scenarios that we hit. So the first one is Black Friday. So the month before Black Friday in marketing is like our most intense month ever, because there's going to be a lot of advertising done to sell things. And so the workload that we have actually entirely doubles. And so we need our pipeline that we have here to be able to double in terms of everything that we're doing. And so with a serverless sort of approach, since we're only paying for what we need and we let the cloud provider just kind of give us more computers as we need it, we don't really have to worry about doubling. We know our costs are going to go up, but we know our revenue is going to be more because we're selling more products, and so everything's fine. With the old way, we might have to provision more machines for the month. We might have to set up more things, et cetera. So also on Black Friday, right after Black Friday comes Cyber Monday. And on Cyber Monday, the amount of online data that we get doubles. Everybody's online on Cyber Monday. And so the same sort of thing. Our data store has to be able to deal with that. Our modeling systems have to be able to deal with that. And so for us to have more serverless sort of support, it really helps us not have to worry about that at all. The next one, Meltdown Inspector, so security issues. And so the cool thing with serverless stuff is you're not running the computers, so nobody can really hack them. And if they did hack them, they're hacking your cloud provider, which is a much scarier thing. And so what's really cool about it, though, is even though you have cloud providers and stuff like that, Meltdown Inspector, when it hit our company, a lot of groups are thinking about how am I going to patch my kernel, how am I going to restart all of my machines, et cetera. When you're using serverless tech, it's just oh, hey, my cloud provider just sent me an email and they said everything's cool. So they already fixed all this stuff. I don't have to worry about it. They're patching all the kernels. They're patching all the like hypervisors and stuff in the background. They're doing it for you. And so big kind of security issues, even major ones that are happening at like the OS level and like the core CPU level, those get handled for you using serverless tech. Going global. So this is always kind of a fun story. A long time ago, when we were starting to go international, and this is pre-Snowden days, groups were just like, hey, we can't store our international data in the United States because the US government's going to like spy on it when it gets transferred over the sea. And we're like, you guys are crazy, but whatever, we'll set up some systems internationally. Turns out that was kind of true. But for us, we can go global in any way. And this is just kind of using the cloud in general. It's pretty awesome. You can set up your whole entire infrastructure elsewhere. And you can do that with like infrastructure as code. And there's a lot of cool tools to do that. But with serverless tech, it makes it even easier. If there's serverless tech that's available in other countries, we can basically take our whole platform and just say, all right, we're going to roll it up and launch it in Ireland, or we're going to launch it in Germany, et cetera. So we can actually take our whole platform, launch it all over the world. And then the last one, scaling our platform. So Oracle and even Oracle Data Cloud, we've acquired a lot of companies, a lot of data, et cetera. So we always have new companies, new tech coming in. A lot of that times, those companies are bringing in tons of data, tons of new processes. By going serverless, we can kind of expand and adapt alongside that, which is awesome. So as much as I'd love to say all of this work was mine, it was actually a lot of everyone focused here. We're the targeting team, so I took everybody axe throwing to see how well they could hit targets. So this is my whole team, and these are the people who are really doing the good work that's behind all of this. Just to show you how good we are at targeting, I have this awesome video. Right on. Yeah, so great team. Everybody put this together, and everybody's been working really hard. And the nice thing is, for this team even, everybody comes in as data scientists, and then I tell them, all right, you're going to be focused for the first 6 months making this system stand up and not fall over anymore. That's not really fulfilling for them. And so going to serverless and being able to say, hey, infrastructure is easy. You can kind of look at a picture of it. Just believe me, it works. Now go read papers. Now go to cool data science stuff. They love it as well. So it's been great for them, too. So that is it. Happy to answer any questions.
As you start to break up your kind of Spark jobs into more of a serverless platform, do you worry about any kind of performance issues there? Because normally, like when you have to, if you tune a Spark app, it's a very careful process, right? But then now you're starting to split it up in different parts. You worry about any kind of SLA stuff there?
Yeah, so kind of, you're saying like if serverless Spark solutions start to exist in that sense. And that's why, for Spark, we're actually still on like a Kubel setup. Spark is one of those things where it's really nice to have the bare metal kind of set up your own containers. But if you think about Spark, like when it runs in like a yarn mode, it is running in a container. And so if a service existed where we could just say we want 12 yarn containers that contain this much memory and this much CPU, potentially it could be good. I guess the one caveat to that I haven't even thought of would be if those containers aren't co-localized on the same machine, you'd start to have shuffling across a network as opposed to in like memory buses and stuff on the own computer. So that could be an issue going forward. So I think it would be one of those trade-offs. It would probably be a big potential speed decrease depending on kind of the type of jobs that you have, but potentially could just be worth it for the scalability in that sense. Awesome. Yeah, so not a lot of tech stuff here, but the idea is just like go, serverless stuff exists, go play with it. It's super fun. Not even for things like this. Like I have a personal website, and every time someone uploads an image, I want to make a thumbnail of it. And you can do all of that not on a server. You can just do it with like, you see an image in this directory, run a little script, and make it turn into a thumbnail. All of that serverless compute. So it's a lot of fun in that sense.